Algorithmic game theory tries to understand systems, also called games, where different agents interact with each other and whose interests are not necessarily aligned. A central notion in this field is that of a Nash equilibrium, that would correspond to a stable outcome of the game. However, not all games possess Nash equilibria. So, how do we characterize those games that do have equilibria? And more importantly, how can we decide whether a given game has an equilibrium? In this talk, we will try to answer some of these questions within the framework of congestion games. Suppose we have a collection of agents that want to move something, either themselves or some data, from one point to another in a network. You can think, for example, of vehicles on a road network, or computers on a computer network. Now, as a designer of such networks, you would like to avoid situations where many users use the same resource at the same time, since this can lead to undesirable outcomes, such as traffic jams or overloaded servers. As it turns out, such systems can be modeled very nicely by congestion games. We can define this type of games formally. We consider a set of players n, each player having a positive weight. We also have a set of resources e. Each resource, also called edge, has a cost or latency function. The argument of this cost is the sum of the weights of the players using that resource. As this is a strategic game, we need to talk about strategies. Each player has a set of possible strategies, which correspond to given subsets of the set of resources E. Note that different players may have different strategy sets. After each player has chosen its strategy, we can define the joint strategy profile as the merge of the strategies of all players. On a given strategy profile, we can then define the load on the resource and the cost of a player. The load of the resource is simply the sum of the weights of the players using that resource, whereas the cost of a player is the sum of the costs on the edges that that player is using on his strategy. For example, suppose we have the following graph with 4 nodes, A, B, C, and D. Here in this graph, we have 2 players, the green player and the red player. The red player would like to connect nodes B and D on the network, and essentially he has 2 strategies. Either he takes the left path, connecting B through A through D, or he takes the right path, connecting through C. Similarly, the green player also has 2 strategies, the top path or the bottom path. Now, after each player has chosen a strategy, there will always be an edge which is being used by both players. And then, let us suppose we define the cost on the edges as follows. The cost of the top left edge is 1 if one player is using it. The cost on the top right edge is 5 if 2 players are using that edge. And the cost on the bottom right edge is 2 if one player is using it. Here, for simplicity, we are assuming that all weights are 1. So the load of an edge is just the number of players using that edge. Now, under this cost structure, we would get that the cost of the green player is 6 and the cost of the red player is 7. Depending on how the cost functions look like on the other edges, it might be worth for green or red to change to another strategy. This, of course, raises the question of whether we can find a strategy profile where no player will gain by deviating. This is the well-known notion of pure Nash equilibria. Nash equilibria kind of correspond to the stable outcomes of our game. Formally, at the Nash equilibria, the cost of player I, when playing strategy Si, is less or equal than the cost of that player if you were to change to any other possible strategy. Here, we use the standard game theoretic notation of S minus I to denote the strategies of the players other than I. In the unweighted case, if all weights are 1, congestion games have very nice properties. Pure Nash equilibria always exist. Not only that, there is an algorithmic flavor to this result, in the sense that they can always be found by best response sequences, which you can think of as local search dynamics. This nice result was proven by Rosenthal in the 70s. Unfortunately, in general congestion games, pure Nash equilibria need not exist, since the weights can be different. Therefore, it makes sense to relax our notion of equilibrium. For example, we could think of mixed Nash equilibria, where players are allowed to randomize over the strategies. For the purposes of this talk, we'll actually look at the notion of approximate equilibrium, or alpha PNE. This means that even though a player may not be playing their best strategy, the cost that they incur is actually within a factor of alpha of the best possible cost. Here alpha is greater or equal than 1 and kind of quantifies how much we are willing to relax our notion of equilibrium. Where alpha equals 1, we get exactly the notion of exact equilibrium. Here are some known results regarding the existence of equilibria in congestion games. First, it was proven, as already mentioned, that exact equilibria need not exist. Counterexamples have been found by Lehmann and Orda, Gomez et al. And Fotakis et al. Moreover, Dunkel and Schulz actually proved NP hardness of the exact decision problem. That is to say, given a congestion game, it is NP hard to decide whether it has an exact equilibrium. An interesting case is that of congestion games with polynomial cost functions. That is to say, the latency of an edge is a polynomial of degree up to d. For polynomial games, we know that alpha PNE exists, where alpha is d factorial due to the work of Clara et al. This was later improved, and now we know that d approximate equilibria always exist. On the other hand, Hansknecht et al. Gave a lower bound and proved that 1.153 equilibria are not guaranteed to exist in polynomial congestion games. In our work, we extend over previous results by showing a lower bound that increases with d. Thus, we now know that alpha equilibria are not guaranteed to exist for alpha smaller than square root d over log d. Not only that, we are able to lift our non-existence result into a hardness result. We also show that it's NP hard to decide whether an alpha approximate equilibria exists, where again alpha lives below the existence bound. Although for this talk we'll focus on polynomial congestion games, we actually have some results for general cost functions. Here, the number of players n is a reasonable quantity of interest in our study. We show positively that n approximate equilibria always exist, and we give a nearly matching lower bound, showing that n over log n approximate equilibria are not guaranteed to exist. And again, this lower bound can be translated into a hardness result. So in general, how do we prove that there are games without equilibria? Well, the main technical idea is to guess a cyclic structure, a structure of strategies such that players are stuck in a loop of best responses. In our construction, we consider the following games with n plus 1 players and 2 times n plus 1 resources. Here we'll take n equals to 3, so that there are 4 players and 8 resources, labeled A0 to AN and B0 to BN. We consider one heavy player with weight 1 with the following 2 strategies. In the A strategy, he'll play all of the A resources, and in the B strategy, he'll play all of the B resources. We also have n light players, each with a smaller weight W. The first light player has two strategies. The A strategy playing A0 and B1, and the B strategy playing B0 and A1. Similarly, the second player can play A0 and B2, or he can play B0 and A2. This goes on, and the last light player can either play A0 and the last of the B resources, or B0 and the last of the A resources. We've defined the players and the strategies, but we need to talk also about the cost functions. In our example, resources A0 and B0 will have a cost function which is a monomial of degree k, where k is smaller than d. As for the other resources, they'll all have a cost which is a monomial of degree d multiplied by some factor beta. Therefore, this gives rise to a family of games, one for each choice of n, w, k, and beta. Next, we want to show that pure Nash equilibria need not exist. To do this, we consider two cases. First, suppose that the heavy player is alone on resource A0. That is to say, all the other players are playing the B strategy. In this situation, we want to show that it is profitable for the heavy player to change the B strategy. By computing the different costs on either strategy, we can actually bound the improvement, giving this quantity that depends on our choice of parameters. In the end, we just want to take alpha, which is smaller than this ratio. On the other hand, suppose now that the heavy player is not alone on resource A0. Therefore, he shares it with another player, say player I. Well, in this case, we need to show that player I is the one that wants to change. He will change from the A strategy to the B strategy. Again, by computing these costs, we can get a lower bound on the improvement ratio. Now, if both cases hold, then we can easily see that there are no approximate equilibria. And in particular, we'll get a cycle of best responses. So here in this example, all the light players would like to change their B strategy, and they do so. And afterwards, the heavy player would also prefer to change the B strategy, since he's alone on resource A0. Then we get a symmetric situation, and again, players will continue to change. Then, to turn this into a lower bound, we want to make sure that our alpha is as large as possible. Therefore, we have converted the study of existence of equilibria into a nonlinear optimization problem, which you can then analyze. For example, by plotting the value of these lower bounds for different values of d, we actually see that it grows. We can prove formally that this function grows like the square root d over ln d. Thus, this gives us a non-existence result on approximate P&E, where alpha grows roughly like the square root of d. Next, we would like to turn this result into a hardness result. To do that, we show that the framework of congestion games is actually quite powerful. So let's suppose we have a circuit such as this, built only with NAND gates for simplicity. How can we emulate the computation of this circuit using a congestion game? Well, the simplest approach is as follows. We define a set of players corresponding to the inputs x1 and x2 of the circuit and the gates of the circuit G1 to G5. Since this is a binary circuit, each player will have essentially two strategies, either the 0 strategy or the 1 strategy. The strategy of a gate corresponds to the value of the output of that gate. Let us zoom in one of these gates and see how to emulate it using a congestion game formulation. On a given gate, we define two resources, the 0 and the 1 resource. Here our players have weight 1. So the 0 strategy of a player will consist of the 0 resources of all gates that player is interacting with, either as an input or as an output. And similarly, the 1 resource would appear in the 1 strategies of the 3 players involved in that gate. So here, for a particular choice of cost functions, in particular monomials of degree d, we can show that at an alpha PNE, the player corresponding to the output of a gate is forced to play the NAND of the players corresponding to the inputs of that gate. And this will be an alpha dominating strategy for alpha smaller than 3 to the d over 2. I should mention here that this coefficient mu is chosen to be such a large enough constant that the costs on gate k will be much larger than the costs of the gates which have a lower index. This is to enforce that we don't really need to care about the lower order gates when we analyze the alpha improving dynamics of gate k. By constructing the game in this manner, we are actually able to show that the congestion game emulates the computation of the circuit. That is, given an input x to the circuit, its output can be obtained as follows. First, we convert the input into a strategy profile on the input players. Then it turns out that there is a unique alpha PNE that corresponds with this strategy profile. In particular, in that alpha PNE, the gate players are forced to obey the NAND semantics of the circuit. Therefore, the strategy on the input players propagates forward into the strategy of all the gate players. At the end, the last player, whose strategy corresponds to the output of the last gate, is forced to play according to Cx, the output of our circuit. We can combine both of the ingredients which we saw to get a hardness result. So suppose on the right we have a game G that does not have an alpha approximate equilibrium. Then, given a circuit, we can define a congestion game as follows. We merge the circuit game, which we saw in the previous part, with a non-existence game. The player corresponding to the output of the circuit will still have 2 strategies. The 0 strategy remains unchanged, but now the 1 strategy is changed. He would play not just the 1 resource of that gate, but also all the resources on the non-existence game. We also extend the non-existence game as follows. First, we add a dummy resource. The players on the original non-existence game are still allowed to play all the strategies that they used to play on G. However, they gain an additional strategy, a dummy strategy, in which they play only on the dummy resource. Now, by choosing an appropriate cost function for the dummy resource and rescaling these games if necessary, we can obtain a game with the following properties. Suppose a circuit has a satisfying assignment. Then it will still be profitable for the output player to play the 1 strategy, regardless of what the players in the non-existence game are doing. In this way, the output player can force the players on the right game to opt out of playing in G, and therefore they will play in the dummy strategy. This will give rise to an alpha PNE. Namely, in this alpha PNE, the inputs of the circuit will play according to the satisfying assignment, all the gates of the circuit will play according to the NAND semantics, the output of the circuit will play the 1 strategy, and the players in the non-existence game will all play the dummy strategy. On the other hand, suppose that the circuit does not have a satisfying assignment. Then player G1 will always play the 0 strategy. Since he will never play on the non-existence game, this means that the players on the non-existence game would now not want to play the dummy strategy. Therefore, they will play on G. And because G does not have an alpha approximate PNE, there is no way that we can extend this into an alpha PNE on the whole game. Therefore, this constitutes a valid reduction. Our circuit has a satisfying assignment if and only if the corresponding game that we have built has an alpha PNE. Since the circuit satisfiability problem is NP-complete, we get our hardness result. If there are congestion games that do not have an alpha PNE, then it is NP hard to decide whether a game has an alpha PNE. By plugging in the non-existence game from part 2, we get that it is NP hard to decide whether a congestion game has an alpha PNE for alpha smaller than square root d over log d. Actually, it is worth mentioning here that due to the properties of our reduction, we actually get hardness of counting. That is, it is also sharply hard to count the number of equilibria of a polynomial congestion game. There are still a few questions left open from this work. First of all, is it possible to narrow down the existence gap and figure out what is the correct threshold at which equilibria are guaranteed to exist? A second question, which I also find quite interesting, is regarding the complexity of finding approximate equilibria when we know that they exist. Here, we actually have some positive results. From the work of Clara et al., we know that one can compute alpha PNE in polynomial time as long as alpha is at least d to the O of d. Note that this exponential guarantee is still very far from the existence guarantee of d. So we might be wondering what will happen in this blue regime here. The reason I find this very interesting is because at the moment we do have a candidate for what this complexity class should look like. We know that there exists a class PLS of polynomial local search problems. Since alpha approximate equilibria can be found by local improving dynamics, at least for alpha greater than d, we know that the computation problem lies in the class PLS. It will be very interesting, therefore, to find a matching hardness result. This will give us a gradation in the complexity of finding approximate equilibria, from NP hardness to PLS hardness to polynomial time as alpha increases. With this talk, we have seen that congestion games provide a natural framework to study competition of players on common resources. Nash equilibria are also important in congestion games for the predictive concept. If we model our system as a game that has Nash equilibria, then we can assume that eventually the players will stabilize at such an equilibrium. Of course, this raises the question of how can we decide whether a game has a Nash equilibrium in the first place. By guessing cyclic structures, we can come up with some non-trivial non-existence bounds. And by harnessing the power of congestion games, in particular by simulating circuits, we can get hardness results. By mathematically analyzing these questions, we can gain a deeper understanding of congestion games and also on the structure of Nash equilibria in general.